Yeah, welcome to this last lecture, the lecture course on quantum gravity. Last time we applied various methods of quantization to black holes. And today we briefly outline another major area of application, which is the universe as a whole, cosmology, and here quantum cosmology. Of course, again, in this 1 hour, I can only give you some introduction. As an appetizer also, if you like, for further studies. So in my book and elsewhere, of course, you find much more details and also all the issues I had to neglect in this short time. Let me start with a quote by Georges Lemaitre. Georges Lemaitre was one of the pioneers of classical cosmology. I mean, the Friedmann-Lemaitre equations you all have learned, and he's also called the father of the Big Bang theory because he was the first in the 1920s who actually related solutions of the Einstein equations in cosmology to real observations, not just, say, to mathematics. And out of this, he developed his ideas of also of a quantum origin of the universe, which, of course, are quite remote from what we're doing here, but still has some condensates of ideas. And this was in 1931. And let me quote him from that article. If the world has begun with a single quantum, the notions of space and time would altogether fail to have any meaning at the beginning. If this suggestion is correct, the beginning of the world happened a little before the beginning of space and time. Of course, you can reflect about the meaning of the language. The beginning of the world happened a little before the beginning of space and time. But here, what he means is actually, this breakdown of concept of the usual concept of space and time. And out of this, he developed his concept of the atom primitive, the primitive atom, but this is more a whole big in history of cosmology, and it's not related to what we do here because this was much earlier than the approaches to quantum gravity we discuss here. Now, how can you hope, to discuss cosmology in quantum gravity? If you recall, classical relativity we apply to the universe as a whole because we impose a so-called cosmological principle to arrive at a very simple ansatz for the space-time metric. Now, the cosmological principle means that the universe roughly on large scales, beyond 100 megaparsecs or so, looks everywhere the same. And this is at least approximately supported by observation. I don't repeat what we did in cosmology. So you make a symmetry reduction, and this we take over to the quantum theory. That is, what we do is actually we use symmetry reduced models. Friedmann cosmology, or you could also say here Robertson-Walker line element, and quantize these restricted models. Of course, it's a general issue whether this is allowed. Whether symmetry reduction commutes with quantization. In general, of course, it's not allowed. We know that, because if you neglect a degree of freedom, then you also neglect its momentum, and this is in conflict with the uncertainty principle. But we also do this in quantum mechanics. For example, in the rigidly rotating body, so we neglect certain degrees of freedom. So we only have maybe rotation degrees, but not others, because they occur at an excitation level that is not relevant. And also here, this is what at least we hope that can be done. Of course, here we don't have many experiments, but it's a matter of belief that also here we can do as in quantum mechanics, to neglect certain degrees of freedom. If you had always to take all degrees of freedom into account, you would not be able to solve quantum mechanical problems because you would have to take all atoms and so on. No? So you have so you make a symmetry reduction. At a classical level. and then you do then a quantization, which means a quantization only of very few degrees of freedom. And you can do that in geometrodynamics with the Wheeler-DeWitt equation. You can also do it in loop quantum gravity. Then you arrive at loop quantum cosmology. You can also do it in string theory. Now, for the restricted time, I will only discuss geometrodynamics, so I apply the Wheeler-DeWitt equation to that. So here I should say we use geometrodynamics. And in fact, this was done already in the first pioneering paper by Bryce-DeWitt, where the Wheeler-DeWitt equation occurred first, together with, Wheeler's paper in 1967. And already Bryce-DeWitt applied then this equation to cosmology. So you can already in that paper see some first applications. Now the terminology may seem a bit strange to you because Wheeler coined the term superspace for the space of all three-dimensional metrics. Now this is of course everything with all degrees of freedom. If you reduce the number of degrees of freedom to very few, then you get a mini version of that. And Charles Meissner, the former student of Wheeler and co-author of that famous book, called it therefore mini superspace. So in 1969. So this is also what you use here since then. So if you hear that first, you think, okay, what is mini super? But it has a clear meaning. It's coming from the superspace, but with restricted number of degrees of freedom. If you're doing, say, spherical symmetry, so this is between full theory and just here homogeneity, then it's sometimes called MIDI superspace. So of course, this also refers to terms of fashion, end of the 1960s, when Meissner coined these words, but it has a clear meaning here. Mini means homogeneous models, quantized homogeneous models. They may be isotropic, they may be anisotropic, but they should be homogeneous. And if there are some inhomogeneity, maybe even if it's only a spherical symmetry, then we call it MIDI superspace model, so that you understand the literature if you read this. Now here, what we will do in geometry dynamics, we study a Friedmann-Lemaitre cosmology. With a scale factor A. So classically, this is A of t. And okay, we should also do some matter. Now, matter in cosmology, we have dust or radiation. But here, to quantize, we should have matter with dynamical degrees of freedom. And so we use, and this is standard, a scalar field as a model for matter. You can use it also to describe dust in a certain limit, but it's much better to have full dynamics. So we have here with scale factor A and homogeneous scalar field phi of t. Of course, then, if it's homogeneous, it's not really a field, no? Because field means something that depends on space, but a homogeneous field is just constant in space, but can depend on time. So after quantization, what is left is, of course, no longer the classical trajectories, but a wave function, psi, and it only has then two degrees of freedom, A and phi. Now, instead of the whole three metric and the matter degrees of freedom, just these two mechanical variables remain. So it's just the psi of A and phi. And as you know, there is no t left. And in the quantum theory, because we have no trajectories, time has vanished, we only have space and spatial degrees of freedom. So you see, already kinematically, we will find a two-dimensional problem, And this makes it possible without mathematical problems to formulate the equations and to give solutions. In some cases, analytic solutions, in other cases, numerical, but there's no problem with functional derivatives and with delta functions or whatever. Now the ansatz, the classical ansatz is here for the Robertson-Walker metric. That the line element, the four-dimensional line element, is ds squared, is minus n squared of t dt squared plus a squared of t d omega 3 squared. Now, okay, you know that. I mean, usually in the cosmology lectures, we said n equals to 1. This is the lapse function, but here, because we are doing quantization, we keep the lapse. You remember, the lapse is responsible for reparameterization of the time, because t is just a parameter, and you're not obliged to take n equals 1. You can take some other function t going to f of t, and this would correspond to a certain choice of n. The shift is no longer here. The shift is responsible for the coordinate transformation in the three-dimensional space, but these are here these fixed three spheres with fixed angles. No? So we freeze in the coordinates on these three spheres. So we don't need a shift because we don't want to have other coordinates. So this is d chi squared plus sine squared chi d theta squared plus sine squared theta d phi squared. And for definiteness, I consider here only a closed universe. So this is why I take here this line element, the three sphere, S3, and which corresponds to k equals 1 in the notation of Friedmann universes k equals 1, minus 1 and 0. Of course, you can do also minus 1 and 0. It's just for definiteness, and because it's a three sphere, we can easily do the mathematics. So no infinite space, just a finite dimensional, three-dimensional sphere. Okay, so I go in some detail to the formalism so that you see how the general formalism that you saw some weeks ago is here applied in a more step-to-step version. So we parallel this in a simpler context so that you really can see that in an example how it works. So you remember we had the three metric and the extrinsic curvature. Okay, out of which you calculate, I mean, the momenta as a linear combination. Now, what is this? What is the three metric is what you read off. This is here the three-dimensional part. So, what is the extrinsic curvature? There you have to look back to our expressions we had some time ago, and so there we had that KAB is 1 over 2n HAB. There was also a part with the shift, but the shift is here 0, so we don't need that. So it's basically the velocities. No? I said before that the k is basically the q dots, and this then gives then the p's in an analogy to p is m times q dot in mechanics. Yeah. So if you insert this here, so these angles are frozen, so the only dynamical degree of freedom is the scale factor. Yeah, there's nothing else here. So this here is the only dynamical degree of freedom. And then, of course, the scalar field. And so this here, if you insert that, then you get this is A dot over A n times H A B. Now you just differentiate, I mean, this here, and this gives this factor 2 cancels, and the n is there. And then you rewrite it in terms of HAB, and this is why I write here in that form. So from this you can also calculate the trace, which occurs here, KAB times HAB is the trace, and if you do that, then you get this is 3 A dot over A times n, and A dot over A is of course an old friend, of in cosmology, it's the Hubble parameter, no? Which gives you the expansion rate. Just here written with a lapse, because usually you set n equal 1, but this here is the Hubble parameter if you allow any time coordinates. So this is 3 times the Hubble parameter. And so you see here a direct intuitive picture of what a second fundamental form K means in cosmology. Now, the Hubble parameter has dimension inverse time, so that means K to the minus 1 has the dimension of time. And it's of time, and it's sometimes called extrinsic time or York time. Extrinsic because it does not follow from the 3 geometry, but it's a classical concept that gives you information about the embedding of the 3 geometry in the 4th dimension. Okay, now we go to the actions and rewrite them in a form such that only the A and the phi appears. And then we will have a very simple mechanical action of a form you know from classical mechanics with a Lagrange function, and then we can directly proceed. So the action, we have a sum of the Einstein-Hilbert action, and I have perhaps briefly mentioned but not discussed too much, a surface term. So we have actually 2 terms, 1 over 16 pi g integral d4 x square root of minus g r minus 2 lambda, no, from gr. And then we have a surface term that I briefly maybe discussed, minus 1 over 8 pi g, and then we have the integral d3x square root of a. Okay. Now, so why that surface term? Even if you have forgotten about it, I can briefly explain, and you will see in the calculation. This Einstein-Hilbert action is second order in the time derivative, so it has not the form that you are familiar from classical mechanics, where you have a q dot square term, which is first order. So you can deal with that, but it's somehow more comfortable to deal with a first order action, because then you can use, all your previous knowledge about that. And one recognizes, and this was recognized by Einstein, that this R has a second derivative, but this is linear. And so if it's linear, you can make a partial integration and put it into a surface term. I will show you. And this is why you can, from the very beginning, add the negative of that surface term, so that the surface term is away, and you just have a first order action. You see it in the example. No? So that is true for the full theory, and it will of course also reflect in that example. This was already noticed by Einstein in 1916, but he wrote this term not in such a neat form, but very explicitly with gammas and so on, and so it was not really, immediately accessible. So it was rediscovered much later in the 1970s, and by Gibbons and Hawking, who wrote it and also there in that form. This is why it's often called the Gibbons-Hawking term, or Gibbons-Hawking-York term, because also York discussed that. Anyway, if we say first go to this here, and we insert now here, for the HAB, what is here, and for the K, what we have here, the trace of the K is that. Then you get, for this integral, I should first maybe write only here this 3-dimensional integral. So you get a cubed. This is the square root of the determinant. No? And you have a squared, a times a squared, and then the square root, which is a cube. And then you have the chi, the theta, the phi, and of course you have to take into account here from the metric, this sine functions here. So you have here sine squared chi and sine theta. Now you're certainly familiar with S2 integrations. This is an S3 integration, so you have here an additional sine squared, but this is in front of the 2, so this is why you have sine to the 4th and the square root, so you have the sine squared. And yeah, so this k, of course, you introduce from here, so this is 3 a dot over an, and so what you get here from this, then this is then the whole, and you can check, is then minus 3 over 8 pi g, so a squared, a dot over n, and then you have this, so the 3 integrations or the 3 angles, so the chi integrations gives you a pi over 2, the theta integration gives you a factor of 2, and the phi integration, I should write here, a small phi to not confuse it with the scalar field, although this danger is very low, the 2 pi, and so you get all in all then minus 3 pi over 4g a dot a squared over n. So that gives you, this here only pi 2 times 2 times 2 pi. Yeah, so these are the 3 angles. So this is chi, this is theta, and this is phi. And this together gives then 2 pi squared, which is the volume of S3, of the unit S3. If you want to keep your model generally and you don't restrict to the closed model, then you can just introduce a volume. Yeah. So in general, write here a volume V0 that gives you just the volume of the 3-dimensional space, and you can do everything here with V0 instead of 2 pi squared. Of course, if your space is infinite, then this volume is infinite. Then you can just keep it as a regularization factor, or you can make space finite. For example, if it's flat, infinite space, you can compactify to a torus, and this is still flat, and it has a finite volume. But this is not difficult here, and I think to keep things simple, I have chosen the case of the 3-sphere, so that 2 pi squared is the volume. Okay, then the main term is here. Okay, here. This again is it's a 4-dimensional integration. So we had before that this can be written as n dt square root of 8 d3x. No, dt d3x, this is d4x, and square root of minus g we had in the general case as n square root of 8 when we made this 3 plus 1 or ADM decomposition. And so this again yields in the integral a cube times 2 pi squared. No? So if you integrate this over, you get again here 2 pi squared, and from that you get the a cube. Now we have, of course, to insert the r in the cosmology or relativity course. When we discuss Robertson-Walker metric, there we calculated this, so I don't repeat this here. So R for Robertson-Walker can be written as 6 over n squared minus n dot over n dot a dot over na plus a double dot over a plus a dot over a squared plus 6 over a squared. In fact, this is here the 3-dimensional Ricci scalar which occurs in the Wheeler-DeWitt equation, the constraint, and these are the kinetic parts or the ones that have derivatives here. You see here, in fact, the second derivative occurs linearly. Fortunately, in contrast here to the first derivative, which occurs here squared, and which gives actually the nonlinearities of the theory. So this you plugged in, And then you get, so this is the Einstein-Hilbert action. So minus 1 over 16 pi g integral d4x square root of minus g r minus 2 lambda, then gives you 3 pi over 4g integral dt n a cube, and then you have n minus n dot a dot over n cube a plus a double dot over n squared a plus a dot squared over n squared a squared plus 1 over a squared minus lambda over 3. No? As you can, if you just collect this together, this here and this, and you multiply by, or you put something outside, a number outside of the integral, this is what you get. Now you see here again this linear second derivative. So we now treat this by partial integration. So here, this here, okay, in the integral, so if we write integral dt a double dot a squared over, together with this, no? So that's these two terms together, a squared over n. No? So I multiply by n a cubed, this is why I get this. And so this is a squared a dot over n. Well, at the boundaries, call it t2 and t1. And then, of course, partial integration means then we have to have an integral with having one derivative to the second term. And then we get minus integral dt a dot d over dt a squared over n. That's what we have. And so the second term here, this is, say, together with the minus, is minus integral dt. Then we have minus 2a dot squared over n plus a dot a squared n dot over n squared. So that's what we have, which together gives a minus 1. So these are the same term because of this here. And so you have minus integral dt a dot a squared, a dot squared, sorry, a over n squared. Yeah, I hope I have everything here. So this n over n, sorry, n. Yeah. So then this together with this term here, this first term, if you multiply by that, then you get also this n squared. And we have, if you have a cube, then we get the 8 squared. So these two then cancel, I hope. Minus, I'll just see here the sign, I hope. Now I'm just puzzled, because these two terms should cancel, and when they do, but I now have here some minus issue which I just recognize. No, right now. And then here, sorry, this is 1, minus 2 is minus 1, and this minus gives a plus 1, sorry. And this cancels the minus. Sometimes one is too close here at the blackboard. Yeah, so as they must, no, of course this is prepared, so as they must, these two terms cancel. And so this means that we have then here for the Einstein-Hilbert action 3 pi over 4g integral dtn. So the a cube is then also taken into account, minus a dot squared over n squared plus a minus lambda over 3 a cube. And then we have the surface term here, which comes from this integration here. And if you take these prefactors into account, then you have minus plus 3 pi over 4g a squared a dot over n t2 t1 and so this should then directly cancel with this here. This here is the surface term, so this cancels that. I mean, this is not an accident, because this here is chosen to do that purpose. Yeah? So, I mean, we notice, I mean, if you did never know about that and you did this manipulation, then you would find this surface term. And if you want to have an action without surface term and only first order derivative, then you just add this and to cancel that, because this will not change the equation of motion, a boundary term. The Euler-Lagrange equation will be still the same. It's just that the boundary conditions, of course, change. And this can be subtle. So we have then the gravitational action. This is then the Einstein-Hilbert action rewritten. Is then, I call it just SG, gravitational, which is 1/2 integral dtn minus a dot squared over n squared plus a minus lambda a cube third. So that's one of the two building stones for the calculations. And you see here again what you already know from the full theory, that here in the kinetic term is a minus. So if you write this down in classical mechanics, on exam in classical mechanics, you will not get a good grade for the kinetic term negative. But here in gravity it's correct, and it comes from this negative direction in the de Witt metric. The de Witt metric has also other degrees of freedom, gravitational, they come with a plus. But the one that comes with a minus has to do with the size of the sweet geometry and the volume, and this is the only thing that is left, is from the scale factor a or a cube. If you had a non-closed model, then you would have here this factor k, which is here set equal to 1, but if you have a flat universe, then this is just absent, and if it's an open universe, then this changes sign. No? So in principle you would have here k times a, and k is 1 minus 1, 0, but I restricted for simplicity to a equals 1. But the other cases can be accommodated also. Yeah, so that's the gravitational action. So let me write down now the matter action, and if we have both, then we can do the canonical formalism. So for matter, I mean it's a field, but I call it matter. Matter means everything apart from gravity, and we have the phi field, which we take the matter action Sm is 1/2 integral d for x square root of minus g, and then we have minus g mu nu d mu phi d nu phi minus m squared phi squared. So this is so-called free field, but free means it's in interaction with gravity, but it has no self-interaction. Self-interactions can be accommodated in a straightforward way, and that you write here maybe a plus phi to the 4 or whatever interaction you like. Yeah, and so again the same calculations. So this here is again n dt, and it gives in the integration then 2 pi squared a cube, from the integration over the 3 sphere. And here this phi depends only on time. So the space derivative in the sum are 0. And so you get from here only 1 over n squared phi dot squared. I mean, recall that g 0, 0 is minus n 1 over n squared. So because of that, we make life simpler and rescale the field by a factor so that we have a canonical form. So rescale phi by phi going to phi over square root of 2 times pi. Why? Because then I do not give the field a new name, no phi tilde or something like that. So that you have then Sm is 1/2, so you have the canonical factor 1/2 integral dt na cube, and you have phi dot squared over n squared minus m squared phi squared. So this is then your matter model, and the total action is then the sum of the gravitational one Sg, which is here down, and this matter action. So that you have then S is Sg plus Sm. Yeah, and you can write it in a condensed way. You can call it is the integral dt of a Lagrange function that depends on q's and q dots, where okay, these are, or I should write maybe qa and qa dot, so that I mean q1 is a and q2 is phi. So you have a two-dimensional problem, and you can call these 2 degrees of freedom a and phi. You can call q1 and q2, and so you can write this as the integral dt n, the Labs function, and then as 1/2 gab q a dot q b dot over n squared minus the potential that depends on all the q's. Just without index means all the q's. And this JAB, if you look for the sum of the two, this SM, and this you must just collect the kinetic terms. Look what is in front of a dot squared and what is in front of phi dot squared, and then you see that this is JAB is minus a 0, 0 is this matrix. And this is the analog of the de Wit metric in mini superspace, so it's also called a mini superspace de Wit metric. That's the metric on the configuration space, on this two-dimensional configuration space of A and phi. And you see explicitly here its indefinite nature. So that's the mini superspace de Wit metric. So square root of minus g, I mean the determinant, this is the determinant of g. I should write determinant of GAB turns out to be a squared. If you calculate, it's indefinite, this is y squared of minus g. Now let's turn on the machinery, which is the canonical formalism. We have done that in the full. Now you see it in the example. So we have here the canonical formalism. So of course the Labs function appears undifferentiated. So if you want to define the momentum corresponding to the labs, it's just 0, because dl over dn dot is 0. Yeah, so Pn, which is defined as dl over dn dot, is 0, and we can write in Dirac's notation this sign because it means it's a constraint. So the momenta are constrained to 0. No other momenta to n are allowed. The others are not constrained, so Pa is dl over dA dot, which is minus AA dot over n, and P phi is dl over d phi dot, which is A cube phi dot over n. Just following here from the sum of this and this term here. Next thing then, when you have the momenta, is making the Legendre transform to obtain the Hamiltonian. Now, from this then you get a Hamiltonian. H is Pn n dot plus Pa A dot plus P phi dot minus L. And if you insert then here, this is 0 as a constraint, and here you, as usual, you substitute the velocities by the momenta. So using this, you write instead of the velocities the PAs and P phis respectively, and you insert here L and also do this replacement. So you get n over 2 minus Pa squared over A plus P phi squared over A cube minus A plus lambda A cube over 3 plus M squared A cube phi squared. And you can write this also in such a compact form as for the Lagrangian by using the inverse of the de Witt metric. So you get n times 1/2 GAB. So with upper indices is the inverse metric PA PB plus V of Q, where you have all these terms here together. No? And you see here this is quadratic. In the momenta, in mechanics, you have the P squared over 2m. There the de Witt metric is trivial, it's just the 1 over 2m, the mass. But here this depends on A. No? So this is the inverse de Witt mini superspace metric. Okay, the potential V of Q is a potential that depends on A and phi, and it's 1/2 minus A plus lambda A cube over 3 plus M squared A cube phi squared. And of course you could also, instead of M squared phi squared, write any potential. Yeah, so you could generalize this to writing A cube and some function of phi that you believe is your model. But we will not do that, no? But you could do that. Okay, so we have this primary constraint, and as in the full theory, we demand that it be preserved. So we demand that the Poisson bracket with Hamiltonian, which gives the time evolution, vanishes as a constraint. And because this just gives dH over dN, and the n is here in front only, so it gives here that all of this is 0. And this means that the Hamiltonian itself is 0, as in the full theory. I have shown that in the full theory. And this is the Hamiltonian constraint. The momentum constraints are identically fulfilled because of the symmetry. So we have no shift, and the momentum constraints are just give 0 equals 0. So there is no point to discuss them. Now, instead of the Hamiltonian constraint, which is a local constraint in the full zero at each space point, we have now just one equation, one mechanical equation. So you see that this is much simpler than in the full theory. Now, at the Lagrangian level, this would correspond to the equation a dot squared. If you write this in terms of velocities instead of momenta, you would get this a squared phi dot squared plus lambda over 3 plus m squared phi squared, and this is just the Friedmann equation or Friedmann-Lemaitre equation. If you have here, I mean, the row or twice the row. No, but here it's, of course, it's dynamical because it's a field. But so this is the Lagrange version, and this corresponds to the Friedmann, or one of the Friedmann-Lemaitre equations. Yeah, as it must, I mean, the formalism must be consistent, of course. Now, we have concentrated on A. Of course, we should also get an equation for phi. And this you get from here, from the Euler-Lagrange equations. You just write d over dt, dl over dq q dot minus dl over dq is 0 mechanics. And you write this here, and then you get the equation for phi. From here, then you get that phi double dot plus 3a dot over a phi dot plus m squared phi is equal to 0. No, so if there were no universe here, or if phi were not coupled to the cosmological expansion, then this term would be absent, and you would just have the oscillator equation, which is clear because it's a quadratic action, and so in a sense it's an oscillator, harmonic oscillator action. But here we have this additional term, which is crucial, of course, in cosmology. So it's like a friction term, phi dot, and the parameter is the Hubble parameter. No? So then, or maybe I should, probably there's an n here missing, I guess, but n is set here equal to 1. Okay, so then this would be just 3. Okay, I don't want to confuse the h's, but this is Hubble times phi dot, Hubble parameter times phi dot. So the Hubble parameter acts as a friction constant in this equation. Okay, before going to the quantization, what can we learn about classical solutions? Okay, it depends on the potential, and analytically you can solve this coupled system only for vanishing mass m equals 0 of the field. If not, then you can easily solve it numerically and plot the curves. That's not a big deal. So analytically possible m equals 0, and then it turns out, okay, if m equals 0, let's have a look into it. Then this is absent here, and we have only p phi, or in the Lagrangian we have only phi dot squared. So phi is a so-called cyclical variable. A cyclical variable in mechanics is one where only the derivative appears and not the variable itself, and it means that the corresponding momentum is conserved from the Euler-Lagrange equation. So then we have, p phi is a. No, this is here, and I set here n equals to 1 again, and this is then constant, and let me call it k. So this we know, and we can solve this. So phi of a in the special case of vanishing cosmological constant by an elementary function. So this is plus minus 1/2 r equals cosine hyperbolic or area function k over a squared. And this would then look like this, phi and a, so it would look like this. So roughly, then you can plot it, and it looks perhaps nicer. And so this maximum here is the square root of k. So k, of course, should be positive then here. Now, so that would be the solution of that coupled A and phi field in configuration space. And it's a recollapsing model because we have a closed universe, so it expands, has this maximum. But it's not in T, no? It's, in a sense, phi acts here as your clock. For m unequals to 0, one can have a numerical solution. This, by the way, corresponds to what is called the model of chaotic inflation that André Linde, 1983, developed to describe, the cosmic inflation, which is by now ruled out experimentally, but which is a nice model. And so this is here a phi. So you can try, with a computer just to program this in. This is with Mathematica, it's not very difficult. And then you should find something that oscillates here around and then recollapses asymmetrically in general. No? So you have here, if you start here, then it would correspond to the inflation. Then here it oscillates here with a frequency related to the mass, and then it recollapses. Okay, now we are interested, of course, more in the quantization than in this maybe also nice classical solutions. And maybe I do that here. So the quantization. And we follow the general prescription of geometrodynamics. That is, we have this classical constraint, and this is the only constraint that is left. And turn this into an operator and apply this on a wave function that depends on A and phi, and that this is 0. So that's the mini superspace Wheeler-DeWitt equation, and it's just one equation, one partial differential equation. So that's the central equation you have to discuss. Of course, when you write down here a quantum equation, there arises the issue of factor ordering. Yeah, classically, of course, the ordering between p's and q's does not matter. These are just numbers. But when you turn p's and q's into operators, they do no longer commute. So classically, you can, of course, this depends on the q's here. You can multiply this here in between. Yeah, that's up to you. But if you then substitute the p's by derivatives, h bar over I times d over dq, then if this is here, it hits also the metric. In ordinary quantum mechanics, you have 1 over 2m, and so it's not directly obvious that there's a factor ordering problem, although there is one. If you go, say, to polar coordinates, you see it. But here you have it. So what is the factor ordering that you choose? Of course, this is an open issue because we have no experiment that would fix it. But we are pragmatic and choose, in a sense, the same factor ordering that is successful in ordinary quantum mechanics. Non-ordinary quantum mechanics, maybe you usually do not learn about that because we have distinguished coordinates, namely the inertial coordinates or the Cartesian coordinates, x, y, and z. And so we just write the kinetic term p squared over 2m in Cartesian coordinates then as minus h bar squared over 2m, and you have the Laplacian, which is d squared dx squared, and so on. And then from this you can transform, say, to polar coordinates or to elliptic coordinates, whatever you like. And what is behind that is a so-called covariant prescription of the kinetic term, also called Laplace-Beltrami term, so that you can write it in a form that is covariant with respect to changes of vector ordering, or changes, I should say, changes of configuration variables. No? So demand that the kinetic term be invariant under transformations in configuration space. That is, you make the prescription that this term GAB, PA, PB in the quantum theory is realized by minus h bar squared times the Laplace-Beltrami operator, which is defined as minus h bar squared over square root of minus g, so that's the determinant of the de Witt metric, and then dA square root of minus g, GAB, dB. So that's perhaps familiar to you from the relativity course in differential geometry. There we had also a covariant D'Alembertian or wave operator. If you have a wave equation in curved space-time and you want to have a kinetic term, a D'Alembert, that is covariant under transformations, yeah, in configuration space, then you also have these determinant terms. Yeah, I mean, in flat space, this is just absent, and then you have just the GAB and the second derivative if this is a constant, but here the ordering matters. So that's a proposal. I mean, other people may say, no, we want it simpler, we just write this to the left, and we just have here second derivatives without additional first derivatives. You can do that, but you have a slightly different differential equation and also then different solutions. Now, if you change in the Schrödinger equation the vector ordering, so maybe you write by hand, you can write the first order derivative in x, then of course you change the solution, so you get a different spectrum for the hydrogen atom. Okay, here we have no spectra where we can, of course, check the correctness. But I think it's a well-motivated prescription. And here, if you insert this here, you get h bar squared over a squared d over dA, d over dA minus h bar squared over a cube d squared over d phi squared. So that's what a kinetic term then looks like. You see you have here, this looks very familiar, minus, okay, some factor, but second derivative, like in the Schrödinger. But here, of course, you get here, when you hit that, also a first derivative. And also recall that here we have a different signs here. Sometimes it's useful to use, instead of a, another variable called alpha, that is defined as follows. So often we can some reference scale that sometimes is set equal to 1, but for dimensional reasons it should be there times e to the alpha. No? So because this here goes from 0 to infinity, the scale factor, and this here goes from minus infinity to infinity. So it's often for calculations better to have a variable that goes, that lives in the full range of the real axis. And if you do that, then you get the Wheeler-de Witt equation, finally. You write this as a factor in front, and you have h bar squared, d squared. Oh, I think I have maybe forgotten on the way that I choose a very special condition for the gravitational constant, not to set it equal to 1, but to a certain, I think I forget, so the gravitational constant I said here G is 3 pi over 2. But of course you could take it also into account. For example, in the semi-classical approximation, you need to take it into account here. We are interested in the structure of the equations. Yeah, minus h bar squared d squared over d phi squared, then minus a naught to the 4 alpha plus a naught to the 6 e to the 6 alpha, and then we have m squared phi squared plus lambda over 3 times psi of alpha, and phi is equal to 0. So that's then the form that is mostly used and popular. Okay, you can multiply this through because this is not 0, and then it's a way. Why do I nevertheless keep that? Is because somehow this contributes to the De Witt metric. So if you're interested in the De Witt metric and how it enters, then this factor is there. But just for the solutions, it does not matter. No, so you see, I mean, without that term, you would just have a free wave equation with alpha somehow having, I mean, this has a different sign, so this plays the role of a time. Yeah, okay, we have only 2 degrees of freedom, but if you added higher degrees of freedom, they would all come with minus. Even if you had some gravitational anisotropies, they would come with minus. So it's really this variable, as we know from the full theory, that corresponds to the intrinsic time. So time, t is absent, but in a sense from the 3-dimensional geometry, from the space, you get a variable that in the quantum equation looks like as if it played the role of time. No? This is why it's called also intrinsic time. Yeah, you can also call it a Klein-Gordon equation with if this is time and this is, or if this were time, this were space, with a time and space dependent potential. So it's not a Schrödinger equation. The Wheeler-De Witt equation is something different. It has the form of a Schrödinger. If you write it just h psi equals 0, it looks like a zero energy Schrödinger equation, but the h has this indefinite kinetic term, so it's more like a Klein-Gordon equation. So alpha here is also the a, or a is called then the intrinsic time. So this gives the dynamics. So even if I mean h psi equals 0 is static, it has this dynamics with respect to the intrinsic time, which is the size of the universe. What else is here important to notice is, I mean, this is the potential. So the potential V of alpha and phi is minus a naught to the 4 e to the 4 alpha plus e to the 6, well, plus a naught to the 6 e to the 6 alpha m squared phi squared plus lambda over 3. Now what I want to emphasize is here, this alpha enters explicitly. So if you call alpha intrinsic time, replacing ordinary time, you see that this is asymmetric with respect to reversal of time. So this is unequals v of minus alpha of phi. So this for the first time gives you then the possibility to recover the direction of time in our universe, the origin of irreversibility. I mean, to the end, the second law of thermodynamics from a fundamental dynamics. No? If you instead have a t, that this, where Einstein equations go from t to minus t, you have this intrinsic time, I mean the small universe and the large universe, but the theory is not invariant under, in a sense, going from a small universe to a big universe or vice versa. And also if you write the Wheeler-De Witt equation in the form, maybe I go here. So Wheeler-De Witt equation you can write in this form minus h bar squared over times d squared over d alpha squared. Psi is the rest, maybe I call it just h alpha squared psi, so it has the form of a Schrödinger equation squared in a sense. So if you took the square root, you would have the I h bar d over the alpha here of that operator, and you would have the Hamiltonian. But this is no longer positive definite, not positive definite. So that would mean, the square root of that in the Schrödinger sense is not self-adjoint. And this would also mean that the evolution with respect to the intrinsic time alpha is not unitary. No unitary evolution with respect to alpha, which is not a problem because alpha is not an external time t that is outside everything. No, it's part of the dynamics. And it's like if you have in quantum mechanics one of the x's as an alpha, and of course you have no unitarity with respect to an x. No, the external time has vanished. And if you consider alpha from this formal analogy as an intrinsic time, then definitely the evolution in the Schrödinger sense would not be unitary. And you see in this example also the problems of reduced quantization that we discussed in chapter 5. To remind you, a reduced quantization, if you first solve the constraint classically, so that it's no longer there, and then you quantize, in the solutions. So if you did that here, you see what happens. So recognize here problems with reduced quantization. What we had in chapter 5. No? So let us choose classically a time parameter. So choose classically. Classically we can do that. A is equal to t, and solve h equals 0 with respect to the momentum. Now, perhaps you recall this from the free particle that we did long ago when we elevated the time to a dynamical variable, and reduced means going the opposite, calling one of the variables time, and so that you get PA plus the rest is as a constraint so that you get such a then you could quantize this in the Schrödinger way, but of course then you have to deal with this HA, or maybe I have here the A, not the alpha. If you do that here and solve the classical constraint, which is the one here, then what you would get is here that the H alpha is plus or minus the square root of p phi squared over t squared minus t squared plus m squared phi squared t to the fourth plus lambda over 3 t to the fourth. So that would be your Hamiltonian in the Schrödinger equation. So would you really like to deal with such an equation, with such a Hamiltonian here, which has a square root, so it's not self-adjoint? It also explicitly time dependent. You will have a hard time, to solve it and to understand it. So you see that in general, reduced quantization leads to a complicated equation, much more complicated than the Wheeler-DeWitt equation, which is a linear equation. No square roots and so on. But if you classically choose some time, and you could also choose phi equals t, or you could PA equal t, whatever you like as a time, and but you typically get a complicated thing, and this is why I would say that this reduced quantization in general does not work. It works in in particular examples very nicely, but in general, so even in cosmology, it has these square roots, and yeah, it's awful. For our example of the massless particle, that this is the classical solution, recall. And how does the solution of the Wheeler-DeWitt equation look for that? So, solution of Wheeler-DeWitt equation for m equals 0 and also lambda equals 0. And I said also h bar equal 1, just that you see the structure of the equation. Then we have d squared over d alpha squared minus d squared over d phi squared minus e to the 4 alpha. Yeah, also I said a0 to 1. Just that you see the structure. It's not so important. They have all the factors here. Psi of alpha and phi equals 0. So that's what you have to solve. But if you, for example, want to have a wave packet that follows this narrowly, this equilibrium universe, then you have, of course, to impose the boundary condition that psi go to 0 for a to infinity, because otherwise you would, this is a classically forbidden regime, otherwise you would get exponentially growing pieces of psi in the classical forbidden region. Yeah. So impose psi alpha phi to 0, alpha to infinity, no? To avoid pieces in classically forbidden region. Of course, you will have some tails going there, some exponentially decaying tails, but not increasing ones. Okay, so you get a separating solution then. So separating solution which is psi k of alpha phi is okay. The phi part is just there's no potential, so you can use, I mean, for this part just a plain wave, but then you have this differential equation here, and this is a Bessel equation that leads to a Bessel function, and you can convince yourself that this is, I think it's also called Macdonald function, k I k over 2 of e to the 2 alpha over 2. No? I mean, you can make a rewriting, and then this would correspond to an x to the 4. And if you look into the tables or wherever, you know, there are these k and I and other Bessel functions. It belongs to that class of differential equations. So that's the separating solution. And of course, a general solution you can get by superposition. General solution psi of alpha and phi. Then you sum from minus infinity to infinity dk a of k with some function a of k psi k of alpha and phi. No? So as you do say already in quantum mechanics 1, when you discuss the free particle and dispersion of the wave packet, you superpose with a certain factor a of k to get, say, a Gaussian wave packet, and then see how it propagates. No? So here, for wave packet solution, choose, for example, a of k is a proportion with the appropriate prefactor, of course, but with this Gaussian part that the k here is concentrated with some width around k bar. And then this you can, of course, calculate. It's exactly doable. And then you get here that, okay, you get a real and imaginary part. Let me write down the real part of psi. which is okay, some constant, which I call like that. Then cosine, well, c k bar. K bar is the momentum around which it is peaked. Cosine of f k bar of alpha and phi e to the minus b squared over 2 phi plus 1/2 area cosine hyperbolic k bar over e to the 2 alpha squared plus c k bar cosine t k bar alpha phi times e to the minus b squared over 2 phi minus 1/2 area cos k bar over e to the alpha squared. No? So you see there's a sum of two Gaussians, each of which here is peaked around values of phi, giving by plus or minus this here. And if you compare this to the classical solution, then you see these are just the two possible classical solutions, which together give here this expansion and recollapse. No? So you see here, this is the quantum solution. It's then just the sum of two wave packets that are concentrated around this classical solution. So what I want to show with that is, of course, that you can here in quantum cosmology use similar methods that you have learned in quantum mechanics. Yeah, you have a different wave equation, but you can write solutions, you can superpose them, you can construct wave packets, you can also discuss things like dispersion of wave packets and so on and so forth. I mean, which I will not in this 10 minutes, of course, review. So they are concentrated around classical trajectories, concentrated around classical trajectory. Okay, there we had this curled k here, which is classically it's the conserved momentum, and here this is just here our k bar here around which we, concentrated here the wave packet, which is here this k bar, and it classically just means the conserved momentum. So you see the analogy to the free particle, where also the momentum is conserved, and you just have this dispersion. And here you don't have a dispersion here in that simple case, but in more complicated models, which I have myself also discussed long ago, for example, in the massive case, where you can do it partly only numerically, you find dispersions, for example. Which means that, okay, then this simple particle concept does not survive, as you know, because particles' trajectories are only limiting cases. And in general, in quantum theory, you have wave functions. They can be superposed and spread and tunnel and all these kind of things. Here, one can also discuss a very general feature which is very important for the understanding of time and the concept of time. So look at the following. So if we have a classical model like the one above, but it can be any other, that classically in this two-dimensional configuration space describes an expanding universe with a maximum and a recollapse. Of course, nowadays the real universe observation seems that it does not recollapse, but nevertheless it's an important conceptual feature. And you don't know, if there is some dark energy, it can also maybe recollapse. So it has here a maximum, and it has here, say you start here from okay, maybe not the Big Bang itself, but very small a, and you expand, and then you can recollapse. Okay, this arrow is of course artificial, because there's no direction in that a phi. You could also start from here, which would be the big crunch, and call this Big Bang. So classically, if you say choose your initial conditions here, and solve it, maybe on the computer. Then you would call this recollapsing piece just the successor or the deterministic successor of the expanding piece. No? The universe expands here, has a maximum, and recollapses. If you chose here the initial condition, it would be like that. Not so in the quantum sphere. Now, if you want to construct a wave packet that follows this, so we have the classical trajectory, maybe here indicated, that is dots, and we will now have a wave packet. Now, wave packet means, okay, usually in Schrödinger equation we would have a wave packet here, and maybe we evolve it here, but we have no external time, and there is no trajectory. So if you want to have a wave packet that is concentrated around this, we have to use, the Wheeler-de Witt equation, but the Wheeler-de Witt equation has this hyperbolic structure. Hyperbolic means that you have here an indefinite kinetic term, and for hyperbolic equation, usually you make initial conditions at constant t, which is here constant a or constant alpha, also the derivative. Yeah, so you would make here the initial conditions here. But then you would have to put a wave packet here and here. Yeah? And the Wheeler-de Witt equation you solve then with respect to a or alpha, which means the evolution is in this direction, from small a to large a. So in this sense, that what was classically the recollapsing packet was, with respect to intrinsic time, must be already there in the initial condition. So Big Bang and Big Crunch are in the quantum theory not really distinguishable, no? Because there is no parameter that distinguishes this from this, because there's no direction of time or whatever. So recollapsing part is deterministic successor of expanding part. No? And so here recollapsing, in quotes, because there is no classical part, recollapsing part must be present in the initial condition. No? So the quantum theory only distinguishes between smaller a and larger a, but not between the ends of a classical trajectory, which is no longer there. No? So you have no longer Big Bang, Big Crunch separately, but one common Big Brunch, or however we would call it. Yeah. Okay, so time, seminar time goes to my end, also the lecture, and maybe I will not erase one blackboard, but maybe I will finish by having maybe a brief mentioning of other issues that are the topic of quantum cosmology. So you can see here already in this simple case what is done. Yeah, you have this mini superspace Wheeler-de Witt equation. This is for Friedmann-Lemaitre model. You can also introduce anisotropies. These are so-called Bianchi universes, and try to give solutions. You can do just mathematical investigations about the differential equations, but you can also do, physical questions and take this as a laboratory for the full quantum gravity, where, okay, you have complicated functional differential equations, but here you can see more clearly what is time, what are maybe the issues with the inner product, which I have not discussed here. So, what are interesting topics? Of course, the topic of boundary conditions. Here, they already enter here, in this picture, but there are famous boundary conditions in the literature. Maybe the most famous one, because one of the authors is most famous, namely Hawking, the Hartle-Hawking boundary or no boundary proposal, which would deserve an extra lecture at least. There's also the other boundary condition. One is called the tunneling condition that directly mimics, say, alpha decay in quantum mechanics. But boundary conditions in cosmology, and especially in quantum cosmology, are certainly different from laboratory situations because we cannot prepare some initial state or whatever. So that's a deep issue, and I mean, related to that is the question of singularity avoidance. And there are papers, also we in our group have contributed to that and discussed models where singularity is avoided in the following sense, that classically you have a Big Bang, say, at A equals 0, that the solution of the Wheeler-DeWitt equation has the property that psi is 0 at where classically is the Big Bang. So psi equals 0 would mean, at least naively, probability is 0. That is, if your wave packet would never be able to recollapse, say, to a singularity or emerge from a singularity, you would just go to 0. And you would have just a quantum region, no classical. No? So, at least in models, yes, in models. One is far away here from having theorems like the classical singularity theorems, of course. Then the origin of the error of time I briefly mentioned. And there are some, at least 10 tentative steps in showing how this is achieved via this asymmetry here in the intrinsic time. That the universe, the quantum universe for small scale factors looks very different than from large scale factor. But again, this would be another topic. Also, the issue of what is a probability for the wave function in the cosmological case, or I would say interpretation of psi. I mean, I have been circumvented this here because I have the equations, I have solved the equations, but usually you learn in quantum mechanics 1 that psi gives the probability amplitude for finding an electron here in a box or whatever, but what does it mean here? So tendency is toward conditional probabilities and also probabilities that emerge in a semi-classical limit, as I did some weeks ago, the semi-classical approximation, but you find different opinions on that. And it's not clear that this psi here has the same probability interpretation or has a probability interpretation at all compared to quantum mechanics. So it could be, and already Bryce-DeWitt has stated that, could be that probabilities only emerge here when time emerges as an approximate concept. So that time and unitarity, which is conservation of probability, emerge together in a sense. And that here at a fundamental level there's something different. And also, I mean, the question of decoherence, which you perhaps have heard in ordinary quantum mechanics, which is the mechanism so that you understand how from a quantum system you get classical appearances. Yeah, so why do you not observe a Schrödinger cat that you can generate in principle, but you don't observe it? Macroscopic superpositions, and also in principle you have macroscopic superpositions even more extreme here than cats. I mean, whole universes. So that's also an issue, and also plays a role for the quantum fluctuations in the inflationary universe. And so it's just a small door I open for many problems. I mean, of course, I can easily say that because if one has already worked on it for a couple of years, of course, then you had time to study this, but maybe you feel motivated at least to look into some of these questions. Okay, that brings me then to the end of that lecture course. So that I hope that you got an idea of what is done in quantum gravity, even if time here is limited, and I could only give an introduction and a review of some approaches. But I hope at least that from this you can in an easy way can have access to more advanced literature and understand more advanced literature. Yeah, so at the end I also want to thank my PhD student Dadevik Vardanian, the person behind the camera. Without her, it would not work. Then maybe she can briefly come, that at least you see her once. So thank you also. No? So we have done this. So bye-bye, and see you again at other occasions.